Okay, so we're going to get started. So this is introduction to, that is not correct. Hold on. Am I on the correct workshop? Yeah, I am. Okay. Copied everything over, forgot to change the title slide. Okay, there we go. So this workshop, we're doing a brief introduction for communication protocols. This will be particularly helpful when we get into some of the later workshops that are coming up in the next 2 weeks. I know Adam will be doing console hacking, and console hacking relies a lot on these protocols, and especially when we get into embedded systems and even FPGAs, these may come up again. If not the specific protocols, at least the concepts in those will definitely be important. So let's get into it. Kind of three general sections for this workshop. We're going to start off with just some basics of communication, just to get you guys familiar. Then we'll talk more about the actual electrical concepts that are used, to actually implement those communication systems. And then finally, we'll talk about some communication protocols. So here, I always like to start out whenever I'm talking about communication systems. I like to start off with the fundamental model of communication. So over here, you have your source that then sends over the communication channel. It sends it using a transmitter. It sends a modulated message. Modulation, you can think of it almost like encoding. So you're encoding that message to then be sent over the specific channel. You then have a receiver that receives that signal, and then it sends that demodulated message or that decoded message into a sync, so into wherever the one destination. So this is how we actually achieve communication. This can be both wired or wireless. So the channel could be, an Ethernet cable. It could be a frequency over, the Wi-Fi communication. Could be a wireless transmitter, wire transmitter, fiber optic transmitter, any of those. So this kind of underlies all of those different methods of communication. We'll be focusing on digital communication, which operates on binary, so the high and low voltages that correspond to them. Analog communication is widely used. However, we won't be covering that typically because with analog communication, especially like radio communication, that is kind of its own beast. And we'll be focusing right now just on digital communication. How most of you, show of hands, how many of you are familiar with binary, ASCII, different kinds of data representation? All right, good. So I won't go too much into that. Binary is 0 and 1s. We can use that to represent different things. So ASCII can be used for text, for representing text. The standards and data types determine what that binary represents. So for example, my specific string of binary, this could be, if this was a character, that probably wouldn't be a readable character because that ASCII, the readable character is in like the 70 to 90 range, I think. So that probably wouldn't be a readable character, but that would be some kind of character that ASCII could represent. And then as an integer, we could read that as a number. So that's what that's 0, 2, 4, 8, 12, 16, or base 2. It's 32. You can see just with a simple string of binary, we can represent multiple things. The important thing is that the data represents what you want it to represent. So in this case, we could represent it as text, we could represent it as a number, we could have it represent, an RGB value that an LED is using a light up to display a pixel on your screen. So ultimately in communication, we want to focus on what it's representing and not, what's specifically on the information. From the last workshop, we did cover a little bit of transistors and logic gates. They're the fundamental building blocks that make up the systems that can then process this information. So in the last workshop, we talked about how you can use logic gates, transistors to build up bigger components that will then take these binary representations, these zeros and ones, and actually process them and use them in a physical circuit. And then we can also represent it as bait octal, hexadecimal, or even in decimal, so different numerical too. Is binary, octal, hexadecimal, are those familiar to you guys? Okay, good. Okay, so I'm not going to go too much into that. This mostly just goes over different how binary works. So I think you're all familiar with bytes, different sizes. Yeah, I think it should be good. And modern computers, we typically they're 64-bit processors. So because they're 64-bit processors, that allows them to process a larger chunk of data when compared to a 32-bit processor. Common example of that is like a 32-bit processor. The limit for the amount of memory you can have on a 32-bit machine is like 4 gigs, because that's how much 32 bits can represent. Whereas with 64 bits, you don't really have a tangible limit to your amount of memory, at least for right now. When we get into exabyte scale memory, then we'll have to start worrying about it, but not right now. And again, this is just an example of some different ways you represent the numbers. Everybody good with this? Okay. I'm going a little fast just because right now these are a lot of the basics. I just wanted to make sure everybody had a nice foundation in, because these will come back a little bit once we get into some more advanced concepts with communication. I mentioned already we have 2 different types of communication that we tend to focus on. So there's wire line channels, which could be anything from coaxial cable, Ethernet, or even optical fibers. And then we have the wireless channel, so your Wi-Fi, Bluetooth, radio. Some of them are point-to-point connections. So for example, if I took a fiber optic cable and I connected it from a transceiver to another transceiver across a long distance, that would be a point-to-point connection. Whereas some of them operate in broadcast mode. So for example, a Wi-Fi transmitter would be a broadcasting system, because essentially it's just broadcasting this information out into the air, and then it encodes it in a specific way that whatever needs to receive that broadcast can then receive it. When we're determining what system to use, there are a lot of factors that come into play. So your cost, the complexity, reliability, and even the transmission speed and range. So for example, let's see, transmission speed, range is probably the biggest one, especially when we're working with them. For example, there's like a show of hands, who thinks wireless would have a longer range than wire? Why do you think that?
Since wireless, we're talking about sort of a Bluetooth connection, and those go really far. So
yeah, you just have a really long wire.
You can have a really long wire.
You just have a 1,000,000,000-inch wire. Don't they have them on the Atlantic Ocean, undersea cables to much of?
I omitted the slide at the beginning because I figured this wouldn't come up, but actually it did come up. It was a history of telecommunication. They did lay really long copper cables that they had active amplification in those cables. Yeah, with a wireless connection, you can use a radio. Oh, isn't also condense radio off satellite? It is, yeah. You can actually, I know particularly with certain frequencies, ham radio operators, you can bounce radio waves off of asteroids or even the moon. They'll actually reflect, and then you can use that to go around the Earth, and you can't go through the Earth because radio waves don't go through a solid chunk of material. But yeah, you can reflect them. It honestly, yeah, the range argument is really tough because for example, with wired, fiber optics can go an incredible distance. But also, if you have a satellite that is, doing wireless communication, that can also go a great distance. So you can see with different communication strategies, there's a bunch of trade-offs. Like for example, fiber optics compared to launching a satellite would be pretty cheap in comparison. but compared to like an Ethernet cable, fiber optics are normally much more expensive, at least for the technology that you need to implement them. This is a really big concept I wanted to touch on before we got into some communication protocols. It's parallel versus serial communication. How many of you are familiar with serial versus parallel? No? Okay, good. So with parallel communication, you essentially, if you imagine different lanes of communication, parallel, you're sending information over those lanes. So the reason it's called parallel is because you have multiple lanes of communication that each are carrying some information. So for instance, this could carry some information. So that would be an example of like a parallel communication system. A serial communication system will only consist of one or maybe two channels. So serial would just be this, and then all of your information is just being sent right down that serial communication. In terms of modern communication systems, serial is a lot more prevalent. We'll get into that in the next slide. In particular, because it's very space efficient. Because for parallel, you would need, like, say it's like a 16-lane parallel communication system. You would need 16 traces on a circuit board, 16 wires to communicate that. Serial, you would only need like one or two. Now, initially, how many of you think parallel would be faster than serial? Parallel faster than serial? Okay, good. So here, yeah. So this is just a more detailed example. In this case, so when you see MSB and LSB, MSB means most significant bit, LSB means least significant bit. For example, when I was doing this example where I was translating the binary to a number, this would be the significant bit. Yeah, good. That basically just means what we're looking at first. So in this case, LSB is what we're looking at first, and it's the least significant because it has the lowest value. It's either a 0 or a 1. Most significant bit, we're looking at this. This can either be 0 or I think that's 32. Yeah. So that's more significant than the first one. In terms of communication channels, that basically just means kind of where we start, where we're looking at reading a value. In this case, each lane can correspond to one bit and the lanes operate in parallel. In this case, each bit follows along in series. So for example, if you take the string of 0, 1, 1, 3 zeros, and then 2 ones, that'd be represented in parallel. And then this would be how it's represented in series. Good so far? Nice. Okay. Noise in EMI. There we go. Okay. So for one of the big things that especially we're going to talk about when we get into the security implications of this is noise and interference. So for noise in communication is any unwanted disturbance. So this could come from either a property of the actual channel you're working with. So for example, Wi-Fi, the noise could come from any of the other radio signals in the air interacting with that Wi-Fi signal. Or it could be some external source of noise. So actually that example I gave was an example of external noise. And a property of the communication medium, like for a big thing with wireless is when you're going a long distance, there's going to be more noise because you're just interacting with more air molecules. You're going a longer distance. That would be an example of a property of the actual channel itself. There's also electromagnetic interference, which is any external disturbance that can affect the system through added noise to the system. The main difference, they're similar but different. The main difference between noise and electromagnetic interference is noise is from like a natural source. Interference is from a man-made source. So noise would be from, for example, like radiation when you're in space that can affect, a wireless communication. When you're dealing with interference, you could think of like when you have a circuit, if there's any like changing currents or voltage around that. Like say, for example, you have a really fast memory chip. Within the memory chip, if it's switching really, really fast, that can cause disturbances to other memory cells that then that would be a case of interference. Actually, there is, and I don't know if I can pull that up. There is an exploit where that is actually used to create faults. Called, nope, that's PCI leach. Hold on.
What the order is it?
Oh, of that, yeah. So I keep everything straight. There we go. Yeah, this one. Yep. So if you actually just repeatedly access a row of memory, you can cause bit flips, just based on interference. And we all know bit flips are not very great when you're dealing with digital systems because they can cause a bunch of errors, and if not accounted for, it can mess with stuff really bad. So that would be an example of where actually interference is being used as a method of attack. There we go. So now we're actually going to get into what communication protocols are. So what I gave you up until now is just a bunch of tools that we're going to use to then analyze the communication protocols. I'm sorry if this is boring so far. I apologize, but I just wanted to give you the information beforehand. So then when I get to this stuff, if I didn't give that beforehand, we'd have to go back and then review that. So if it seemed a little just disjointed and kind of boring, that may be why. But here, we'll get to that in a second. So you can think of a communication protocol as almost like the grammar for different electronic systems to talk. You can imagine how bad it would be if we set up digital systems and then they just didn't agree on how they were taught. Like one would be speaking English, one would be speaking French, and everything would be garbled in the middle, and then nothing would get done. So we have standards organizations. A popular one are like IEEE and ISO. They make a lot of these standards. They work with the engineers and the manufacturers to then create the standards so that things can talk effectively. You can imagine how bad it would be if every chip manufacturer had a different protocol. Like nothing would ever get done.
Pretty sure that's what's happening with USB-C, right?
Oh, we're going to get to USB.
Yeah.
So we're going to talk about USB. Yeah. Whenever I mention a communication bus, you can think of that as the actual channel that we're using to communicate. So if we go back to this, the bus in this case would be the channel in the communication system. For those that arrive late, this is the fundamental model of communication. This just shows how you go from a source to a destination over a given medium. Good. Okay. There we go. Good. Yes. Yeah. So the protocols can specify, yeah, they do specify the hardware, usually in the form of that communication bus. And they do occasionally specify the software as well. USB in particular, the protocol will specify the software because USB is very dependent on the software, whereas some of the other protocols are getting to particularly rely on the hardware architecture to create their communication system. So they are a mix of hardware and software that are then used to create the protocol. And typically the protocol that's actually used on a system is dictated by what's available on the actual chips in that system. So for example, if you had a sensor or microcontrollers or different kinds of memory, they'll use specific protocols that when people were designing the circuit, they would have to implement that communication protocol in their system. So for example, when we get to some of the protocols here, like if you have a sensor that uses I2C, you can't have that talk to an SPI microcontroller unless it has like an I2C communication system. Again, similar with think of like the languages, like you can't have English and French talking to each other. Here we go. So this is a popular communication protocol. This is one of the first of the examples that we're going to do. In this case, the bus is actually 2 wires. And it's a bidirectional communication protocol. So that means on the bus, we can have one device talking to another device, while also having that device talk to the other. So in this case, the SDA and SCL, SDA means serial data, SCL means serial clock. Are you guys are familiar with like what a clock is? Where it has a, I've seen some confused looks. Okay. Okay, so we will. Okay. Let's see. Oh God, this is gonna be the wrong. Nope. Okay. Yeah. I would. No. No, not your alarm clock. It's this. Okay. Here we go. Good.
Even though I'm not sure, it does have.
So a clock is typically a signal. In this case, it's normally a digital square wave going from up down. Think of it like a drum for electrons. Think of it as it's just repeatedly switching up and down, and that creates your timing. But for example, because it's a wave, the gap between here and here, that's period. So then that period can then be used to sync up the devices. So for example, a common method is on every rising edge. So every time the clock is going from low to high, that's when communication can happen, is on that rising edge. That's how it syncs up. And the reason that's important is because if you had 2 devices that weren't synced up correctly, they wouldn't be sending information at the correct times. So then stuff will get garbled. So for example, if I go back to I squared C, if I can find the tab. Maybe? Yes, here we go. The reason I squared C has that clock is because if we didn't, then on that serial data line, let's say this device sent information at the same time that this device sent information, it would corrupt itself because it's literally it's the same electrical connection. So if they both send information, it's gonna be bad. They're like some bad stuff will happen.
So
Yeah.
how does it know that it's time to respond? Can send that to the
Yeah, what's up?
What this clock does and what kind of information it needs.
So the clock in this case, on the actual clock line, it's just this. It's just an up and down signal that its entire job is just to synchronize when information is going to be sent. So in this case, yeah. So it's doing is just switching between 0 and 1 at fixed intervals. And the device will then use that switching signal because that switching signal is shared between the 2 devices or however many devices you're communicating with. You can see the serial clock line is connected between all the different devices. And because the protocol implements this, they all know to look for that clock line. They all know that that's there and that it's connected. So then the device will look at that line, see the changing signal. And it'll see, oh, well, the clock just changed from 0 to 1, which means now it's time to communicate. Another thing that they do too, which was Mohammed asked, how do they know when to send stuff? I squared C, it implements, so there's a master device and then a bunch of slave devices. In this case, the master device would be like a microcontroller. So that's what's actually doing the sending and receiving. And then the slave devices are, for example, sensors or something that's being controlled by the microcontroller. I know master and slave wording that's bad. Like I know that's not great wording. Yeah, I know. That's not what they call it. I'm sorry. You can think of this as main and secondary. I know that's typically what they call it now. So the main device and then your secondary devices. The main device will actually pull the communication line low. Let's see. In this case, the people who were at the last one, the basic electronics, do you remember what these are? Resistors, yeah. These are what are called pull-up resistors, because you can see they're connected to a positive voltage. So this means normally both of these lines are pulled hot, so they're pulled to a logic level of 1. So if we graph what the communication line looks like, so this is going to be the SDA signal. The SDA signal is going to be at a logic level 1 because it's being pulled up until the the main device then pulls it low by grounding it. So you can think of this device is actually going to take the SDA line and ground it. And that's going to send it to a logic level 0. And that initial change is what signals for the communication to occur. Once that happens, then it can then send its commands based on how the I2C protocol did. Does that make sense? No, not at all. Okay.
It's grounds that holds it down.
Yeah. So for 0, 1. So when we think of 1 and 0, you can also think of them as high voltage and low voltage. Are you familiar with high and low voltages? Okay. So typically, like for example, this could be 5 volts, and this could be 0 volts. What ground is 0 volts. So this is the symbol for ground. Ground just means 0 volts. And when we're dealing with logic systems, it also means logic level 0. And then when we're dealing with logic systems, plus 5 volts is the same thing as 1. Okay. Does that make sense? Cool. So that's why when I say the master, the main device grounds it, that's why you're seeing that change from a 1 to a 0. And then you can start getting your communication. Because then all of the secondary devices then know that communication is happening, because all of the other devices are still connected to that line, so they can still see that information. They'll see the 0 going, the 1 change to a 0. They'll know to look for that, and then they'll know to see, oh, now it's going to be sending its command. It's going to be sending a command. Oh, device 1, I need you to send your information. So the reason this system works is because the main device is able to control the communication bus, and because of the clock, they know when to send that information.
After you ground it, what did you make them?
This just shows that the digital representation can vary between 0 and 1. So for example, whenever it wanted to send, it could send like an integer, it could send a number, and this just means a bunch of different. Because now this is the point where communication is happening. So this is where the actual data is being sent. So after this, just think of this as your data is happening right in.
Just that.
What do you, the data? In this case, the data would be sent from the main device. So
Oh,
then it's for think of like an Arduino, like a microcontroller. Do you know what that is? Not really. Think of like a computer. Like just think of like a computer sending information. When the computer sends that or grounds that signal, so it sends it to 0, then that information is then being sent from the original device. And then that's being sent out on that communication line. A little bit better? Cool. Are there any other questions about this one? Okay. This one's the hardest because it's the first example. I'm going to try moving on to another one that I think will be a little easier to understand. Yeah.
So it's bidirectional, right?
Yeah.
How many go about like the other side?
So the main device is controlling that bus, but for example, within, after it starts the communication, this data could actually be a command. And that command could be, I want this device to then send information across the bus. And then that command will then allow for that other direction of data to happen. Because by default, this device is sending data to all of these devices. And then depending on how it controls the bus, this device can then send information.
So basically the main device is pulling. The device is on.
Yeah, that's a great way to think about it. Yeah. Yeah, so you can think about how the main device is basically asking each of these devices for their information. And it'll send that information based on when the clock signal dictates. So that's the reason there needs to be two communication lines is, and this is a serial communication line. So if there's data is being sent across that one wire, it's not being sent across multiple different. So that's why there's two communication lines, one for the clock signal and then one for the actual data. So this synchronizes the communication and then this allows for the communication. I don't want to get caught up too much in the actual implementation of them because, this is a cybersecurity workshop. So I want to get to how we're actually going to start working with these. So can I try moving on to one other and then we'll see if, because this one, it's a little weird. It's a little weird, but I started out with the simpler one. The next one might be slightly more complicated, but I think it'll be a little easier to understand. So this is the serial peripheral interface or SPI. This is really common. I'd say I2C and SPI, other than USB, are very, very common for electronic communication. This is a high-speed communication protocol. So the other one, I2C, is not designed to be very high speed. You can see it's about, in the kilobits to maybe megabits per second range. SPI, you can go really fast with this. It's full duplex communication, which means that data, unlike I2C, where data can only be sent in one direction or the other, SPI, you can send it in multiple directions. So you can send it both directions simultaneously. And we do have the controlling device and the secondary devices. And the way it does is it actually separates it out into two different lanes. So you have your, they're called master out, slave in, master in, slave out. Again, I apologize for the wording. That's just how they set it up. Yeah, and so I think of them, in this case, they actually call it a serial data in and serial data out. So in this case, this is the secondary device. So the serial data out is going out of the device towards the controller. And then serial data in, it's receiving information. So it's going from the controller down to the device. And you can actually just follow the arrow. So a dot means they're connected. So for the controller, it's sending information out to this device, to this device, to this device, into their input. And then each of these devices are sending information out to the controlling device. So that's how it establishes that bidirectional communication. Does that make sense? Okay. Now, you may be wondering, well, if they're all connected to the same input and output lines, how do they actually tell which one is which? That's done using the chip select line. Basically, what they are is, think of them almost as like a clock line, where they're acting as the synchronization for the protocol, where if the chip select, for example, if this chip select line goes high, then that device will then be active. So you can see this actually has 3 different chip select lines on the controlling device, and each of those control one of the secondary devices. So if this line becomes a logic 1, then this device will then be communicating. If this becomes a logic 1, then that device will communicate. So
Wait, so what's the SCN?
That's the clock. That is the clock signal. Yeah. So that again, that's this. So that's just the drum beat. That's the on off. That's synchronizing the communication. The reason that's important is, say for example, these are expecting like at their default communication speed. Say these are three different sensors. This sensor is communicating at 9600 bits per second. This one's communicating at 3200 bits per second. This one's communicating at 115,000. Each of these could have their own internal speeds, but then the controlling device will then send out its clock signal at the speed that it intends to communicate at. It could be 96,000 bits per second. The devices will then see that clock signal and adjust their communication speed accordingly to match that if they can. So that's another reason why we need that signal, because if devices are communicating at different speeds, it's almost like they're talking the foreign language. There's just going to be a bunch of gibberish. Good. That's okay. Does this kind of help with the other one as well? This kind of makes some of the stuff in I2C a little bit more clear as well. This one's a little weird. I'm going to be honest. The universal asynchronous receiver transmitter, because it combines both parallel and serial communication. So in this case, this is the actual representation of it. It's called asynchronous because it doesn't need a clock. So this one, there is no clock signal. It's just sending information. The reason that works is because the actual devices that are sending and receiving the information do so through two in-between chips. So in this case, this is the receiver chip, this is the transmitter chip. That's not the actual senders and receivers. Think of this as one computer, think of this as another computer. These are what are actually performing the communications, and they can synchronize themselves. They know how to communicate with each other, so they don't need a clock signal in order to be able to perform that communication. They can just send information back and forth across the transmit and receive. And it's relatively fast. It's a medium speed signal. These are typically used. You'll find these a lot if you want to communicate with an embedded system from an actual computer. So this isn't typically done like from a microcontroller to a microcontroller. This is typically done like from a computer down to an embedded system. When I say embedded system, think like a small embedded device, like in like any smart device that you have. You can think of an embedded system. I like to think of them as like your car's information system. That would be like embedded system. It has its own computer in there, and there are ways to interact. There's some input and output. So whenever you think embedded system, think like a car's computers.
There is I don't know if you know about that, like Xbox, like the drone controllers. They use this protocol to communicate to like a Raspberry Pi.
Yeah, so that's a good example. Think of like the computer on a drone. If you want to communicate out with that, and they use your to communicate with to another system. The actual information it contains, it is sent in packets, so that's similar to, if you know computer networking, that's similar to the packets that are sent over computer network. They have the start bit. Well, the start bit you can think of as like a 0 could be a start bit, like 0 in I2C was the start bit, because when the data sees 0, it knows that's when the communication will start. The data bits, and then the parity bit. Parity bit, think of it as like an error correcting bit. So that's beyond the scope of this workshop. Just saying that that's an extra bit that we include just to make sure that the information is valid. And then the stop it. So a stop it is just another control bit. So say, for example, after you see that length of information, you see a 0, that's when the devices know the communication is stopped. Does this make a little sense? Good. Okay. Any questions so far? Anything we've covered? Anything at all? Okay. Okay. How many of you know what this is? I think a few of you may have seen these. maybe not. You know what this is, yeah,
We have some in the hackerspace.
we do, yeah. So this is basically like before we had USB. This was like pre-USB. So this is RS-232. RS stands for registered standard, so that's just how they labeled it. It is a serial communication standard, so think, only one communication channel rather than many. And actually the protocol defines the cabling, the connectors, and the signaling specifications for this system. So it's not just the electrical connections, but also the mechanical and the cabling as well. The way it represents ones and zeros is a little unique. A one is a negative voltage and a zero is a positive voltage. And the way we actually translate those is we use driver circuits, or just think of them as like in the UR1, you have a transmitter and a receiver chip. Think of those as like the translators. So think of them as like going from French to English and English to French. That's essentially what these do. So the driver circuits convert the RS-232 language back to, your digital 0 to 5 volt language. And then there have been incremental improvements and revisions to the standard, but because it's a very large connector and because it has relatively low data rates, we've phased that out in favor of USB. But you do still see these a lot, especially with industrial control systems, lab equipment, anything that doesn't want to rely on USB or Ethernet will have one of these. Even server equipment. Server equipment will have RS-232 as like a control interface. So it's very useful to know what's going on in this, because then you can communicate with a bunch of different things that you might see when you're dealing with certain cybersecurity events. Like, for example, if you were doing a pen test on a company and you had physical access to their server room, you could communicate with the server over RS-232 and send it control commands. Like, oh, let's shut the server down. Were you going? You're something different. So even though it is old, it is still used a bit. That's why I wanted to include it, just because it is a semi-popular standard. Another thing, how many do you guys know VGA, like the thing like the projectors use? This looks similar to VGA. It's not VGA. Don't try to plug them in together. Yeah, there's they look very similar. The way I always tell it, RS-232 has 2 rows, VGA has 3 rows. They look really similar. Like shockingly similar to each other.
What the other are on the phone, or is it just like that?
They're not dead. They actually, I think, within the original standard, and this is the smaller version of the connector. They have the 9-pin one, and then there's also like a 20-pin connector as well for the standard. I think they had like these extra pins are other communication channels or other specific control signals. So if you wanted to implement those, you could, but all you need for communication is your 2 communication channels and then ground. But I think in here somewhere there is another communication channel. Good question. In this case for RS-232, it's just binary information. So not really audio or video. It could be, but it's not really used for that. Some connectors that are used for like audio or video that have like multiple. Well, HDMI one that can do audio, video, and networking. You might be familiar with like the RCA or component connectors, like the big multicolored ones you plug into the back of the TV. Those do audio and video. I believe those are analog standards. Not big. So they would use instead of like ones and zeros, they would use actual analog signals across. Yeah, exactly. Yeah. Make sense so far? We good? Okay. last one. Oh, last one, I promise. Okay. This one's the fun one. All right. How many of you know how many of you know what USB is? Everybody. Yeah. The one major thing with USB is that it's gone through many revisions. Like the USB 1.0 standard, all the way back in 1996. It just had the Type A and Type B. How many of you have seen the Type B connector? Oh, you're getting that. Okay, nice. Yeah, that's your printer for felony. The main reason they kept on iterating it was for two reasons. One was size. You can actually see the connectors are getting smaller and smaller. And USB-C is getting your really tiny connectors. And then of course speed. So 1.0 you've got only 12 megabits per second. Nowadays you've got you can go up to 40 gigabits per second. You have a really big USB. I have some gripes with USB. The one thing is they didn't do a really great job of backwards compatibility. I mean, on the main one they do it. You can plug in a USB 3 and USB 2, but they just invented a bunch of connectors that really only had like a few years of life before we went to USB-C. Another big thing with them is their naming schemes and how their standards are implemented are really weird. Like I think there's they have like USB 3.0 and 3.1 and 3.2, but they changed their naming system a bunch of times. It's weird. All you really need to know is for this, it uses basically two different communication channels, one for message pipes and one for stream pipes. The message pipes you can think of that as the control signal, and then the stream pipes are the bulk data transfer one. And the cool thing about USB, like I mentioned earlier, is it relies heavily on software. So say you plug in like a USB-C cable and a USB-C cable. Nowadays with USB-C, that cable could be going into a computer, to a phone, to what else do you plug it? A calculator? I don't know. It could be USB-C can be plugged into a lot of different things. So a big part of USB as part of the protocol that they're worried about is designating which is a host, which is a receiver, and actually classifying those devices. So, are you a computer? Are you a embedded system? It actually has different classes of devices that you can then use to categorize the communication system. So it's a very versatile communication system because of its ability to identify and kind of reconfigure itself in software, even though the actual physical connections aren't changing. That's really it. I'm not going to go too much into the specifics on the actual implementation of USB because that would be its own workshop. But yeah.
So what's the deprecated?
Deprecated, that means, so like for example, with USB 3.0, we no longer use the mini A, mini B, or the other mini connectors. We now solely use USB-C. I guess they got rid of all of the super speed connectors, which were those weird blue ones that were used for a short time. Nowadays with USB-C, I think Thunderbolt and some other signaling standards are used to increase the speed. Okay. So finally, what does any of this have to do with security, Harris? Please get to the point. Already 6:50, but yeah. So the one big reason I wanted to introduce all of these all of these communication protocols, aside of the fact that I think it's pretty cool, is if you have physical access to a device, if you're able to exploit the hardware of that system, oftentimes you can get more control over that system than even if you had full control of the software. Because hardware access gives you a new layer of access that your software sometimes just you can't do. Say for example, you're going to compromise a system over a network. If you had physical access to a device and you were able to modify the network card, for example, or actually access the processor, you could do a lot more with that system than just software control. That's not to say software exploits and what we traditionally factor to cybersecurity isn't important, but when you have physical access and you can actually control a device, especially an embedded device that may not be connected to a network, this becomes very important. So a few things to think about. I never mentioned any real encryption within these protocols because the protocols themselves are unencrypted. Most, these hardware communication protocols don't would provide any specific measures for encryption. They leave that up to, the software and to further layers of the technology stack to implement. But as it is right now, like most communication protocols are unencrypted within a device. So for example, if you wanted to read sensor values from like an I2C system, if you were able to tap into that SDA line and you knew what was going on that bus, you could then read that data because it wouldn't be encrypted. Of course, depending on the device.
But you would have to be like physically there, so.
Yes, you would. Yes, that is one thing with hardware hacking, hardware access. You do need to have physical access. So, for example, with a lot of embedded systems, like you'll have to like have it in front of you. This is not typically done like over a network. You have to have physical access. That's one limitation. But have that physical access, you can do a bunch of this stuff that can give you control very quickly and very reliably. If we mentioned a lot, we talked a lot of synchronous protocols, which are the ones that rely on that clock signal. You can perform a fault injection attack, which we will get into in future workshops, where you can actually change the speed of the clock. You can speed it up or slow it down by small increments. And if you change it fast enough, if you create enough clock jitter, that can cause the communication protocol to mess up. So you can introduce a fault into the system that if you introduce it in the correct way, you can actually create a vulnerability, create an entry point for further exploitation. So that's one example of fault injection attack where you can use the actual timing of the system to create an exploit. Also, there are a lot of fundamental flaws in communication protocols that you can exploit to gain hardware access to the hardware and information. An example I like to use is if you want to perform a man-in-the-middle attack, where if you were to, let's say, you were able to connect right between the two devices, you would essentially be in the middle of those two devices. Or let's say you were on an I2C lane and you were able to mimic the actions of the control device. Well, then maybe you could become the control device for that system. And then all of the information, all of the control of that communication system goes to you because you're now the de facto control device. That would be an example of a man-in-the-middle attack where you're in the middle of the communication. So you're able to then read it, or if you're able to actually inject, malicious information into the system, you can then actually take control of that communication system. This is typically done a lot, especially in networking, wireless networking in particular, because it's very easy to, for example, set up like a fake wireless access point, and then use that wireless access point to then monitor the communication system. That would be an example of a man-in-the-middle attack. We do have about 5 minutes left. If there are any further questions, please feel free to ask. I know that was a lot of information too. I will be posting the slides so you can look over them. And then also I do have afterwards, if you're interested, this looks like a lot. You don't have to read through all of this. This is just a bunch of information. If you're interested in any specific thing we talked about, I provided a bunch of stuff that you can look over at your leisure. So, yeah, that's all I got for you today. In the future, for future workshops, we're going to be getting into wireless security. So actually doing some demos and breaking some wireless systems. And we'll also be going into working with embedded systems and FPGAs and actually seeing how we can perform some hardware attacks on them. So stay tuned. Yeah. Thank you guys. Yeah, we're doing. Thank you.
Ever console. We do just like uploading the software programs.